Okay, so today we'll be introducing physical chemistry and talking about what physical chemistry is about and simple stuff that we can do regarding particles. And so when it comes to physical chemistry, the first thing that you're going to need to remember is Schrodinger's equation. And so you might have heard of Schrodinger from Schrodinger's cat, where the cat is both alive and dead at the same time until you open the box, but this is a little bit different. So this is going to be h hat times psi equals E psi. And so what is H hat, what is psi, and what is E? So as an introduction to physical chemistry, there's something called a wave function. So this would be psi. And what is its purpose, right? Well, a wave function's purpose is basically to describe a particle state. And what does that mean? Well, a particle has, you know, characteristics such as position, right? It can also have momentum and so many other, etc. Parameters. And we need to all condense these parameters into something that, can describe all of them. And so that's what the wave function is basically for. You'll see it get defined as we see with like psi squared and that kind of stuff as a probability density. But as of right now, you can just think of all these characteristics are all condensed and stored in this wave function. Now, what about h hat? Well, h hat is something called an operator. So we'll put h hat. And typically anything that has a hat in physical chemistry will be an operator. And so what is an operator? Well, an operator gets us values from observables. So observables would be like position and momentum. So these are the parameters that we were just now discussing. And so you can imagine if I wanted to get momentum, I would have to um, put p hat as an operator for momentum. And the way how this works is, well, in order to get what the actual momentum of the particle in this wave function is, we have to solve what is an eigenvalue equation. And so you might have seen eigenvalue equations before, especially in regards to matrices. And so you might have seen something like if I have a matrix capital A times x, it equals typically lambda is used for eigenvalues. And so you might have seen something like this, right? Well, we have something similar. And this time it's with operators and observables. So an example would be, for the momentum eigenvalue equation, it would be p hat times psi equals the actual value psi. And so you might see that there's a lot of similarity between um, this this equation and what we have up here in Schrodinger's equation. And so you can imagine that this h hat is basically the operator for E. And what is E? Well, E is the total energy of that particle. And so you might be asking, well, why isn't it E hat, right? Um, well, this special operator actually is called the Hamiltonian. So H hat is the Hamiltonian operator. And it's the operator that acts on the wave function that provides us the total energy. And okay, so now that we've defined what operators are, we can start getting into the nitty-gritty of, what actually is the Hamiltonian. Well, the Hamiltonian, I said, is an operator, right? But what is it equal to? Well, the Hamiltonian is basically equivalent to minus h bar squared. So what is h bar, right? H bar is Planck's constant. You might have guessed that from just the h, but it's also divided by 2 pi. So it's Planck's constant. Here, I'll write this. So h bar equals h divided by 2 pi. And so you'll see a lot of h bars in physical chemistry instead of just Planck's constant. And so I'll be using h bar throughout this series. But it's the Hamiltonian is minus h bar squared over 2m. M is mass. And then we're going to take the partial derivative of with respect to x, and then the second partial derivative with respect to x. And then we also add in v of x. So what is v of x? I already said that this will be describing the total energy of the system. So you can think of this as this is potential energy, and this part is kinetic energy. So it describes the kinetic energy of the system, and this is describing the potential energy of the system. There's also other operators. I already talked about the momentum operator, so we can define what the momentum operator is. The momentum operator is p hat is equivalent to h bar over I, the imaginary I, times partial derivative of x. So I'm saying the partial derivative because for a wave function, it could depend on uh, x, y, z if you're in Cartesian coordinates, and time. But in this series, we'll be considering the wave function as time independent, so no reliance on time, and we'll be taking it in one dimension at first, just as a way to simplify things. So while this is a partial derivative, it will be treated as a total derivative. And yeah, so this is all the operators that you need to know for right now. And we can go ahead and continue on talking about our first problem, which is a free particle in one dimension. Okay, so here, let's start fresh. So we have free particle 1D. Okay, so in one dimension, we only have reliance on x, so we can write that only x dependence. And what does a free particle mean? Well, a free particle means that no forces are acting on the particle. And so what that means is if there's no forces acting on our particle, that means that there's no change in our potential, right? Because we don't have any movement from a force, because force is the derivative of potential energy um, in classical physics. So if the derivative of potential is zero, that means that potential must be a constant. So we know that v of x equals c, and this is because f equals 0, which is equivalent to this. And so v of x equals a constant. Well, if it can be any constant, right, we don't have anything like an initial condition or anything that would allow us to solve for what this constant is. Instead, what we can say is why don't we set our reference point, the constant, as 0, right? It would make things a lot simpler, especially in regards to the Hamiltonian. And so for a free particle in 1D, we'll be treating the potential as 0. And so what that means is that now h hat is equivalent to minus h bar squared over 2m del squared over del x squared. Only the kinetic energy part. Okay, so now what we do is we write Schrodinger's equation. So let's write it all out. So we have minus h bar squared over 2m del squared over del x squared times the wave function, which only depends on x, and that's equivalent to e times the wave function. Let's go ahead and multiply both sides by 2m, divide by h bar squared, and let's get just this part alone so that we can combine the energy with all these constants. So what that means is that we get del squared over del x squared psi of x is equivalent to minus 2m e over h bar squared times psi of x. Okay, so where do we go from here? Well, it seems like this equation is impossible to solve, analytically at least, because we have a psi of x here, but that's a derivative, and then we have another psi of x here with these constants. So how do we solve this? Well, the way how we solve this is basically we can think about this intuitively. We see that if we take the derivative twice with respect to x of this wave function, it somehow is equivalent to, generally equivalent to the original function. And so what that implies is that psi of x, the wave function, must be oscillatory in nature. Okay, so we know that psi of x is oscillatory. So what are all the oscillatory functions it could possibly be? Well, you might have known from your trig classes that sine of x, cosine of x, those are oscillatory. We can also toss in e to the ix. That is also an oscillatory function. And so here we can write our possible psi of x's. These are our candidates that all work to fit Schrodinger's equation. So we have a sine kx, and I'm including the k as a parameter in order to non-dimensionalize whatever is inside of the trig function. And then we also have a times e to the plus or minus, right? We have both options, ikx. So these are all oscillatory. And all three of these solve Schrodinger's equation. So how do we decide which one works? Or maybe all three of them are fine. Well, actually, these two are not valid. And the reason for that is that they don't satisfy this eigenvalue equation. And so you can try. We already stated what p hat was. It was h bar over I del over del x. And so if we try, we'll try with a sine kx. If we try it with this, you can see that without even solving this completely, it won't work. Because if I take the derivative of sine kx, I get a cosine out of this. And there's no possible way that we could make a simple cosine equivalent to a sine on this side. And so there's this can't satisfy the momentum eigenvalue equation. And the opposite is also true for cosine, because if I take the derivative of cosine, I'll get a negative sign on this side, and this side will still be a cosine. And so both of these clearly don't work. You could work through this out if you want and check it. So the only one that actually works is ae to the plus or minus ikx, because if I take the derivative once, I still am left with this general ikx exponent on both sides of this momentum eigenvalue equation. And so what is our goal here, right? Our goal is to figure out what the total energy of the system is. We want to find E. So now that we've isolated what the wave function is, right? We know it's this one. Ae to the plus or minus ikx. Now we can go ahead and solve for E. So let me scroll on down, and let's continue solving for E. So we have minus h bar squared over 2m del squared del x squared AE to the plus or minus IKX. And that's equivalent to E times AE to the plus or minus IKX. I already multiplied this. It's fine. We'll just do the same thing. We'll multiply both sides by the inverse of the constants. So we'll get, we should get minus 2me over h bar squared times, yeah, e to the plus or minus ikx. And this constant can be absorbed. So I'll actually delete this constant. Oh, oh, did not mean to do that. It's fine. This constant basically will come out in the derivative and it'll cancel with this one. Actually, tell you what, I'll write the a here and then this cancels out with this. And so what we're left with is del squared over del x squared times e to the plus or minus ikx equals negative 2me over h bar squared times e to the plus or minus ikx. Okay, so where do we go from here? Well, we need to figure out what E is. So E, remember, is equivalent to kinetic energy, right? Because we said that the reference value for potential energy was 0. And remember that kinetic energy, right? If we remember kinetic energy as half mv squared, and we look at momentum, right? When we look at momentum equals mv, we can write the kinetic energy in terms of momentum. We can write it as equivalent to momentum divided by 2m. And so that's equivalent, or actually momentum squared, sorry. Momentum squared over 2m. And so we can do the same thing for this. So we can now write energy as equivalent to momentum, we'll say the x, divided by 2m. And so if we plug that into this equation, what we end up getting is, if I also take the derivative of this, I'll get a minus k squared e to the plus or minus ikx, and it's equivalent to minus p of x squared over h bar squared times e to the plus or minus ikx. Okay, I'll number this. Okay, so now we have this. And if we solve, right, we can cancel out both of these. And if we solve for k, we get that k equals p of x over h bar. Or we could also write that as p of x is equivalent to kh bar. Okay, so now we know what p of x is. And so we can go back to our energy equation. It was E equals p sub x squared over 2m. So now we know that E is equivalent to kh bar squared over 2m, or k squared h bar squared over 2m. And I should write this as E sub k. So this is what the energy is for a particle, a free particle in one dimension. And this is all because we set our potential reference value as 0. And it's important to check if the possible, psi functions actually satisfy the other eigenvalue equations. Because if we went with a sine kx or cosine kx, we would have ended up getting a completely different E value. But yeah, that's all I have for free particle in 1D. Next video will be about restricted particle movement between two walls. So I'll catch you in that one.